All right. So as promised, we will go ahead and start talking about the electric field. And to do that, we need to talk about sort of where the idea of this field model came from. All right. Um, so the topics we're looking at here are maybe, there we go. So essentially, we're going to talk about the need for a field model, why it's important, the concept of a field model, what it is, and then we'll jump to the electric field itself. And then we'll finish off with talking about some unit vector notation. You all have seen this before, the sort of I hat, J hat, K hat notation, but we're going to talk about how we can incorporate that into the electric field and doing these electric field problems. All right, so why do we need a field model? So electric and magnetic forces, like gravity, are long-range forces. We know that. We talked about gravity. So we have electric, magnetic, and gravitational forces. There's three different forces that are long-range forces, as in they act over a distance. No contact is required for one charged particle, or in any of these forces I've listed, any two particles interacting with each other, any two magnets. No contact is required to exert a force on another object. Okay, so in our case, charged particles, no contact is required for them to interact with each other. So that's what makes these long-range forces. There's no actual physical touching, like when we talked about in thermodynamics, where you get an energy transfer through contact, which would be like heating by conduction. This is not the case here for these long-range forces. That leads us to the question of how do these long-range forces work anyways? And that gets us to this concept of a field. So back in the day, Michael Faraday, who's one of my all-time favorite scientists, Michael Faraday actually sprinkled iron filings over a magnet, and this actually revealed a spatial pattern. So this pattern, it has these regular features in it. They are these curved lines, and that suggests that space itself around the magnet is filled with some sort of magnetic influence. So what we're getting at here is the idea that the area around an object, if this object has some sort of force related to it, the space around the object actually is filled with some sort of influence or some sort of alteration. So this space alteration is actually the mechanism by which long-range forces are exerted. Okay, so we have this link between the two. And you can actually see that a little bit over here. So we have these iron filings and we have this magnet. So we have a magnet here, it's a north pole. The south pole is over here. It's just not in the image. Then we have this additional magnet over here with the south pole, north poles over here. What happens when Faraday sprinkled these iron filings around? He started noticing that they sort of fell on these lines that would run from the poles of the magnet. Even if it's on a different magnet, he noticed that even putting two magnets beside of each other, these lines still form between the north and south poles. He also noticed that in the case of if they had similar poles, so in this first example, we have opposite poles here. But in this second example down here, he noticed that if they were similar poles, they sort of avoided each other. There wasn't really any overlap. But in the end, they would still reach back to their south pole. So these would be like poles or the same poles. Okay. So the whole idea here is that the space, which would be here, here, the space is sort of filled with some sort of force and these magnets are interacting with that thing, that alteration in space. So this whole idea, Faraday's idea, came to be known as a field. And a field actually has a mathematical underpinning here. So um, the term comes from the mathematical definition of a field. And basically, a field in mathematics is simply just a function that assigns a value to every point in space, right? So if you think about it, if you think about the terrain on like a map, you can have north, south, east, west, and a up, down, like if you go up a mountain or down in a valley. So let me make sure I get my right-hand coordinate system set up correctly. Yes, okay, so we could have the x direction this way, y direction this way, z direction this way. So the whole idea here is essentially a function uh, that is a field will tell you for any point you go to. Maybe we go over here, maybe we go to x1, y1, but we're at sea level, so maybe there's no elevation. This point would have some value because it'd be an elevation, but we know that would be 0. We could go up here to another point, x2, y2, z2, right? So now you can imagine we're sort of over in the xy direction, and we're also up in the z direction. You should have 1s on them. So if we go to the second point, x2, y2, z2, perhaps this is our function's giving us the elevation. So this field will be, I don't know, it could be the elevation at Boone, which is 3,333 feet. So this function gives us the obvious. It just tells us what the elevation is at any point on a map. Okay, that's cool. But we could also have other fields. We could have a function that tells us what the electric field is at any point in space. But that's the idea of the mathematical definition of a field. Basically, you plug in coordinates wherever you're at, and it will tell you, it will give you information about the magnitude of a thing, whether it's the elevation or an electric field or a magnetic field. This is the idea of a field, and essentially what Faraday was thinking of when he come up with this whole idea of a field in space or this alteration in space. So in our context, since we're talking about these point particles, a charged particle will cause an alteration everywhere in space. Okay, so just like gravity, doesn't matter how far you get away, it might make gravity really weak, but there's still going to be some sort of non-zero magnitude associated with it. Okay, so if we have one particle, in our case, one charged particle, so if we have Q1 here, and we'll say it's a positive charge, so it's got some magnetic field coming out, or sorry, some electric field coming out in all directions. Other charges respond to the alteration. So if another charge shows up here, Q2, I don't know, it could be positive, maybe it's negative, doesn't matter, but the point is, it's going to react to this field in space, this alteration. So this is the electric field. Okay. Now let's attach some ideas to this electric field, some requirements. Let's give it a bigger, more meaty definition. All right. So with a field model in our situation of electric field, remember we could have other types of fields. We have source charges that alter the space around them by creating an electric field. Okay, so we have to have some sort of cause. Okay, And then a separate charge in the field will experience a force exerted by the field. Okay, so that sort of gets at what I was talking about on the previous slide. So we have to have something that causes the field, Q1. So here's our electric field. We'll get into how to draw these better in a few more slides from now. But for now, just know that this field, when it's positive, radiates out from the particle that's causing it. Okay, so there's our source charge. There should be a C. I'm going to see if I can erase this. There we go. So this is their source. Okay, then we have this separate external charge, Q2. Maybe it's also positive. Okay, so this source, or this influence charge here, Q2, we know it's going to feel a force pointing away from the other positive charge. This one's also positive. Okay, so we know they're going to want to fly apart from each other. But what's doing that is this Q2 is interacting with the field from Q1, and that's what's causing the force, and that's the point of this second bullet point here. Okay, so suppose charge Q experiences an electric force from other charges. If Q moves around, the magnitude and direction of the net force, so all the separate forces will vary. So essentially the F net on Q is a continuous function of all Q's coordinates. So essentially what this is saying is if we were to move Q2 over here or Q2 up here, the whole point is no matter where you move it, there's still going to be some sort of interaction. Always an interaction. Man, I am illiterate. Always an interaction. Okay, so that's where we get the idea, the mathematical idea of the field. So no matter where you move this particle, if it's always going to be somehow in the presence of Q1, then Q2 is always going to feel this force. It's always going to have a magnitude. So this is the idea of the field. So we can define the electric field E at all the values of x, y, z, wherever we decide to put this particle. Okay. Now, when we calculate the electric field, this is where it gets a little weird. But this is our mathematical definition of the electric field. So what this is saying is to get the electric field E, we take the force on some particle. In our case, it was in the last example, it was Q1, Q2. So if we wanted, what we've been doing is if we wanted the electric field here, if we wanted E at Q2, we would take the force that Q2 experiences. We know it's this way since they're both positive. So whatever that force is, we would take that force on Q2 and divide it by Q2. That's what this is telling us here. So that sounds really weird. Like we take the force experienced by the particle and then divide it by the charge of that particle. So why would we want to divide out the charge of the particle? Okay, so let's keep that in the back of our heads, this little weirdness in the math, because we're going to address it here in a few minutes. But for now, we're just going to talk about this equation and sort of what goes into it and the units and things like that. So as you could probably tell, given what goes into this equation, the electric field is a force to charge ratio, right? So the units are newtons per coulomb. So you get some amount of force per charge, okay? Now, if we talk about just the magnitude of E, that's the electric field strength. Obviously, if there was a really strong electric field, we could say that, well, it has a large field strength. If there's a weak electric field, that's a weak field strength. So here we're essentially just talking about how strong that alteration is in space. We can also define the electric field at some point to be a vector. Okay, and that makes sense. If we think about the calculation to get this, I'm going to simplify it. We're literally taking the force on some particle, some charged particle, Q, at some place, and we're just dividing out the charge. This really is just a vector divided by a scalar, and we all know that a vector divided by a scalar, that's still a vector, right? You remember from, if you're taking Calc 3 right now, or even from Physics 1, I pointed out that if you have some sort of vector v, let's make it even more generic, not even a v. Let's call it some vector a, and you scale it by some scalar, so you multiply. The new thing you get is still a vector. So that's why we can actually say that the electric field is still going to be a vector if we calculate it. It still will have a magnitude and it will point in a direction. So the basic idea of the field model that we've been talking about is that the field is an agent. The field is the agent that exerts an electrical force on some charge Q. Okay, so there's three important ideas here that you need to keep in mind. So the electric field is a vector field. That means everywhere you go in space, everywhere you go, depending on what's going on, you're going to have some vector everywhere. Okay, so that's what I mean by a vector field. This EXYZ equation is going to give us the magnitude of a vector at any of these points. And again, this sounds nebulous, but we're going to get to some really good graphics here in a little bit that sort of shows this idea. Okay, so if Q is positive, the electric field vector points in the same direction as the force on the charge, okay? So basically, if we have some sort of vector field here, that's an electric field, and we have some positive Q, well then at this point where Q is, if our force points this way, then our E field will also point this way. And this is true for if our charge inside the E field is positive. Okay? So the electric field is independent of the charge Q. Now we're getting somewhere. This goes back to the thing I told us to keep in our heads for a while, like why do we divide out the Q? Here's why we're getting there, okay? So some electric field is in, so the field, some electric field, I'm just going to draw a simplified E field here. Some electric field is going to be there, whether there's a charge in it or not, okay? So if some charge Q shows up, it's essentially only a probe, okay? It's sort of like a measurement device. Now, we don't care what the value of Q is. We don't care why it's there. That's why we divide it out, okay? This electric field is going to exist. But if we drop a charge in here, so here's my charge Q. I've been using positive charges. Let's just use another positive charge. If I drop this positive charge in there, I only want information about the electric field, right? That's all I want to know about. I'm going to change that so we don't think it's part of the electric field down here in red. I only want to know what the magnitude or the characteristics of E is. So to do that, and I'm going to write this in shorthand, yeah, of course there may be a force on charge Q here, but I want to get rid of it. I want to get that out of there. That's why I divide by the magnitude of Q. So we sort of divide out. We divide out this charge because again, we don't care anything about it. We want to get rid of it in the mathematics. So we divide out by Q because all we're interested in, all we want to know about is the electric field, not the charge that's in the electric field. If we take Q away, that electric field's still going to exist. But if we take Q away, we also lose the instrument that we measure E with. So literally, we're taking some charged particle and we're just going to drop it into an electric field. That's going to allow us to measure the properties of the electric field, but then we have to, in the math, get rid of Q because we don't care about Q itself. We just want the properties of the electric field. And that is what this third bullet point means here, right? So we're going to have two particles, something causing the field, but when we talk about just measuring the electric field, the other particle becomes our test probe, right? That's the thing we're going to dip into the electric field and use to make measurements. All right, so let's let's take all of that description and apply a little bit more math to it. So suppose we have two different charges. So I'm calling them Q and beta because those are two very different symbols. We can keep up with them because they look so different visually. Okay, so we have two charges, Q and beta, that are interacting with one another over some distance r. So we could draw that. We have Q some distance away. We have beta, and they are interacting with each other. So from Coulomb's law, we know that these charges exert forces on each other. You know, I've been calling them positive. I'll just keep calling them positive charges. It's probably a bad habit. We need some examples with negative charges at some point. But so if this is Q and it's positive, and beta is also positive, that means Q is pushing beta this direction. So this is going to be the force of Q on beta. But at the same time, we also will have, let me do blue. We also have beta, which is going to be pushing Q away. So this is going to be the force of beta on Q. Okay, so we have the orange vector, we have the blue vector. Those are our action-interaction pairs. So what if we are interested in the E field generated by beta only? Okay, so we want to know, let's see, this is our generator. Beta is going to generate some electric field, obviously. Q is also generating an electric field, but we don't care about it. We want to know, let's see, it's positive, so it's going to radiate outwards. We want to know some things about this electric field here. Okay, now we know that Q is going to feel this electric field, and we know from that other bullet point that the force that Q experiences is going to be in the same direction. So we know that both F and E are going to be in the same direction here. So how do we figure out information from the electric field generated by beta? So this is the E field by beta. Well, that means we need to pay attention here. Q test, our test particle, is actually just our charge Q, right? That becomes the test particle we want to get rid of. Okay, so that needs to cancel out in the mathematics. So to calculate the electric field generated by beta, we have to put in our Q, which becomes our probe, right? So we calculate the net force, but then we divide out our test charge at our location, right? So this is the test charge at the location we're interested in. Okay. Now from here we can just plug and chug. We know how to calculate the net force because that's just the electrostatic constant times the magnitudes of both charges. Well, it's Q and beta. We have to cancel out our probe charge. Well, we know that's just Q. So Q test and Q cancel out, and that just leaves us with this last statement here. So all we're doing is we're multiplying the electrostatic constant K by the magnitude of the generator of the electric field, because remember, beta is our generator, and then we divide by r squared, that distance. Okay, so this essentially just leaves the electric field strength of charge beta. We could reverse all of this, do this backwards, and actually get the electric field strength of Q at particle beta. That works as well. But the whole point of this entire slide is just to reiterate, even though we have two charges, if we're interested in the electric field of one of them, we have to sort of cancel the other one out because that is our test probe charge. All right. So in summary, the electric field E generated by a charge can be determined using a test charge Q at some point. Right? That's why we cancel it out. Okay, that's the electric field. The force on a test charge can be determined if we rearrange this equation to essentially just solve for F. And to do that, we just multiply Q over. So it turns out if you want the force on the test charge, you just multiply the test charge by the electric field that it's in. Which makes sense, right? There's some electric field here at some point. If we drop in some probe at this point, we don't need to know the value of the probe just to get information about the electric field. It cancels out the math. But if we want to know the force exerted by this electric field on some test charge, then we need to know information about the electric field and that charge we put in there. That's why we go from E to QE if we want to know force. But if we just want to know E, we divide out that the charge of the test point particle. So if Q is positive, the force on Q is in the same direction as E. And if Q is negative, the force is going to be in the opposite direction as E. Okay, so this will be pretty much always true. And this is also the test particle as well. Don't forget. Because sometimes when you're just learning this, it's hard to keep up with which particle is the test particle, which one is generating the field we're interested in. So do keep that in mind. Okay, and over here is just a quick visualization. So essentially, if you have some sort of electric field, you can use 0.1 or 0.2 as probes. If you want the forces, then you can calculate forces, right? Because if you want these forces, then you have to know what the charges are, because that's QE. Again, here we have another point, 0.2. It's experiencing a force. That's going to be QE kind of thing. However, if we want to know what the electric fields are at both of these points, well, then we divide by those charges. Divide by the charges, and notice how we don't have the charge there anymore. It's just a point in space. So these just become points. No charges. That's because we divide by Q, which gets rid of that charge characteristic, but it still gives us information about what the electric field is doing at these two different points. Okay, so that is pretty much what's next. Yeah, okay. Excuse me. Um, so we're getting there. We just have one more example here, I think. Yeah, we're getting there. Super close. Um, so suppose there are two positive charges, Q1 and Q2, and they are a distance away. Okay? So now if we want to calculate the force on these two objects, well, then we would include the charges of Q1 and Q2, and then the force would be away from Q2. So you can see, yes, okay, we're still going. Good, 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 good. Okay. Now, if we wanted the electric field strength at the position of Q1, then we would have to divide out Q1. Okay. So here's the trick. When it comes to a force, you have the interaction of both particles. You need their charges. When it comes to an electric field, you just need one of them. So notice, again, it's sort of the what I call the generator. The generator goes in the mathematics because we want to know, as you can see here, we want to know the electric field at Q1, but we have to use the generator of that field in the math. So if we follow along over here in this in these figures, if we have a point charge here and we want to know what the electric field is, okay, well we can figure that out, but we have to place a test particle in there. We can't just do some sort of magical calculation and know what the field is doing. We have to sample the field there. So we put in a test particle. In this case, it looks like it's Q prime. Okay, so now we drop that in. We have one charge here. We have another charge here. They are separated by some distance r. In this case, if we wanted to know the force, right, because there's a force vector here, they're like charges, they're repelling each other. We have two charges in there now. One of them is our source charge, our generator, so to speak. The other one is our test charge. So if we wanted to calculate the force on the test charge, so this would be the force on Q prime, our test charge. This would be the good old Q and Q prime over R squared, right? Two forces or two charges, we want to know the force. We need both components here. But if we wanted to know the electric field, like down here, so we have this charge, but we only want to know what the E field is, that's when we have to, so this goes from F on Q, this goes to electric field at, so instead of acting on, it's acting at a point, since we're canceling out the test charge. So this is at Q prime. Now we're just going to have the one term in there. So this equation here will tell us what the E field is doing up here. All right, so again, we just include the generator. Now, if we do this everywhere, instead of just calculating at one particular point, we can actually draw a field diagram. Remember I said that the E field is actually a vector field. So quite literally, you can look out on a field of vectors all pointing in a similar direction, okay? So for a point charge, all the field vectors actually point straight away from the charge. Okay, and this is true for a point charge. Um, okay. You'll also notice that the vectors decrease in length due to the inverse square dependence on r. Okay, so let's take a look at that with these positive charges. So notice, I'm going to zoom in, hopefully it works well, good. So you'll notice that we have some distance here, right? That's a 1 over r squared dependence. Well, they're really close, right? All of these here are really close. close. So that means these vectors are going to be really long. Okay, so these are strong vectors because they're longer, bigger magnitude. Well, we could actually move out a little bit. So we can go to these. So these points, these 4 points I've labeled, they're a little bit further away, right? Well, they're further away, which means the force they experience at these points, or the electric field at these points, is going to be a little bit weaker. So these vectors are a little bit shorter. And then we could move yet even further away. So I won't do all of them, but for example, these. See how far away they are? That means these vectors, because there's that 1 over r squared dependence, these vectors are going to be even shorter. The same thing works with negative particles as well. So you can see that this flips the direction of the field. So a negative charge is going to make all of the vectors actually point inwards. So as you get closer, they're going to get stronger. You can see that here. So I think over here I used green for the strongest. So notice how close these points are to the charge. Then if we move out further, like over here, notice how short those vectors are because they are further away from that generating point particle. So this is the picture I promised, or the graphic I promised, where we can actually look at these vector fields, and you get an idea that no matter where you put a particle, you can put a particle here, you can put a particle over here, you can put a particle over here. No matter where you go in XYZ space, you're going to land in this field generated by this particle. You could come way over here if you wanted to, and your E field would be like this tiny little baby vector, but it's still there. Okay. The last new point I wanted to make before the example is essentially just you will see unit vector notation, especially if you want to take a more advanced E&M physics course, if you transfer to a 4-year program, or if you transfer to like an engineering program and you do electrical engineering, you'll actually see some of these calculations use the R hat instead of I hat, J hat, K hat. Um, so it's worth noting that this is something that will pop up from time to time. So a lot of these you'll notice I've been saying if you have two forces, you know, maybe they're positive, they're charge Q, maybe they're the same charge, so I'll label them as Q. You'll notice that when we draw a vector, I've sort of been saying that, well, this is just away from Q, right? That's the direction of the force. So how can we represent the direction of these forces more mathematically? Instead of just saying it's away from Q or toward Q1 or away from beta, that kind of thing. And how we're going to do that is we can take the idea of the I hat, J hat, K hat notation, right, which gives us information the X, Y, and Z directions. And we're going to use that similar idea, but we're going to introduce a new unit vector, R hat. So remember that a unit vector, you'll remember from physics 1, a unit vector has a magnitude of 1. So they really don't muck up your mathematics. They just have this value of 1. So you're multiplying by 1, but it gives you information on direction, right? So it doesn't change the value of any sort of calculation. It just multiplies by 1 and embeds directional information. Okay, so it's got this value or this magnitude of 1, and it points from the origin to a point of interest. Okay, it does not provide information on distance. Its length is always 1. It only provides information about the direction. Okay, so we can rewrite the equation for an electric field at some point away from a charge as this right here. That way, we don't have to worry about where these two particles are. We could have one down here, like I don't know, Q1. We could have one up here, Q2. So we don't have to worry about trying to fit a weird Cartesian coordinate system, right? We just say it's in the r hat direction. Otherwise, we might have to like, drop down a x hat, a y hat, or I hat, j hat, and then it could get weird. So essentially what we're going to do is we're just going to uh, always define these problems as just the distance to those two particles in the r hat direction. Okay, that's going to allow us a little more flexibility when we set up our coordinate systems to actually do these problems. Okay, and speaking of doing problems, we'll take a look at one quick example here just to calculate the magnitudes of fields. Um, and then we'll call it quits after that. So we have a -1 nanocoulomb charged particle located at the origin. That's down here. Looks like the point is not showing up well, so there it is. We also have points 1, 2, and 3. They have the coordinates of 1 centimeter in the x direction and 0 centimeters in the y direction. Okay, so here's my point 1. We have point 2, which is up here at 0x and 1 centimeter y. Then we also have at the other diagonal corner, we have the third location here at 1 centimeter and 1 centimeter. So I'll label these 1 centimeter and 1 centimeter. Notice we only have one charge, right? There's no charges at these corners. Only one charge here. Okay, so now all we need to do is just determine the electric field at these points. Well, we're going to think about this first in terms of magnitudes, okay? Now, just looking at the problem before we try to do math, let's just think about what's going on. We know for a fact that the magnitude of the electric fields at these points, we know that the electric field is radiating out in straight lines from this particle. Okay, that totally makes sense. We know that the distance here is going to be the same as the distance here. So that tells us that the magnitude, so the strength, not the direction, but the strength of the electric field at this first point is going to be the same as the strength of the electric field at this second point because the distances are the same. So the first distance is going to equal second distance. Okay, so I've even got it labeled here in the math. This distance is the same. It's R1 and R2. They're equal. Okay, so let's calculate this strength of the electric field. We know what goes in here first. This is our K value. I've just written it the longhand way because you need to get used to seeing it both ways. But this is our electrostatic constant. Okay, then we multiply by the charge of that generating point charge, which is -1 nanocoulombs, which nano means 10 to the 9th, or 10 to the -9th. Okay, and then we just plug in that distance. Well, it's 1 centimeter. This is true for both points 1 and point 2. Now we plug that in, we can turn the crank, and that gives us a value of 90,000 newtons per coulomb. Remember, this is a ratio. It's the strength you get per some charge. Okay? So if you were to drop in like a 3 coulomb charge in there, right? So just as by the way, if we have this 90,000 Newton per coulomb charge, okay, that's your E field strength. Now, if we dropped in some other charge, like, I don't know, it's totally unrealistic, but like a 2 coulomb charge, that means we could multiply by the charge we dropped in. So this would be our test. That would tell us we would get 180,000 newtons, right? Because this coulombs would cancel. So that's the idea. This just gives you this Newton per Coulomb just tells you the potential force you could have there, depending on what kind of charge you drop in, right? So that's why it's a ratio. It's a force per unit charge. That unit charge is saying like, okay, depending on what charge in coulombs you drop in, you're going to get some sort of force out. So in this case, we dropped in a 2 Coulomb charge, and that gave us some output force. Okay, so you can think about the electric field as like a potential. It's telling you how much energy or how much force is there for you to use, which is why it's a ratio. Okay, so that being said, we figured out what the potential is there, right? The amount of force we could get, which is 90,000. Now we can convert that into good old-fashioned I hat J hat notation. Okay, well for E1, the electric field here at E1, I'm going to change colors. So we'll do this one in green. So for E1 here, we know that the value is 9 to the 4th newtons per coulomb, but we have to think about the direction. So we need to go back to our picture. Well, the direction is actually pointing back toward the origin. Okay, so we're going to need this to be negative 9 times 10 to the 4th newtons per coulomb. We know it's in the x direction, so we can indicate that with our I hat notation. Same thing with E2. If we look at it, we know the magnitude's the same as in the x direction. But we also see that the electric field, based on our picture, because this source charge is negative, based on our picture, we know it's going to be in the negative y direction. Okay, so I'm actually going to switch to orange now. So here's my y direction. We know it's in the negative y direction, and we can indicate that with our j hat notation. Okay, so we got those two taken care of. Now we just need to figure out the magnitude of the electric field at point E. So I will use red for that. So what is this? This one's a little harder because it's got some stuff in the x direction and some stuff in the y direction. Okay, so we can figure out the magnitude first. That's easy. All right, so we have our k value, our electrostatic constant, we have our source charge or our generator charge. Okay, now we just need this value here. That is just from the Pythagorean theorem, right? So I'm just going to write PT. You all know how to do that, and this video is getting a little long, so I'll let you figure that one out. Ooh, this should be R3, by the way. R3 down here. So we plug in our value of R3, turn the crank, and we get this value of 45,000 newtons per coulomb. It's further away, so it should be less. Should be less. Okay. Now we have the magnitude, we just need to get the direction. Now we can do that just by thinking about some angle theta here. Okay. Now, just given the geometry, we know that this is going to be a 45-degree angle, which makes it really easy for us. We can just do cosine of 45 degrees to get the adjacent piece, sine of 45 degrees to get the opposite piece, right? So this is going to be our x, this is going to be our y. So we know the magnitude, we get the x component and indicate that by I hat notation. We know the magnitude, we get the y component, and we indicate that by j hat notation. So here, both pieces are pointing in the negative x direction and negative y direction. We can see that from the picture. And because of the 45-degree angle, we know that each component is equal to each other because of the symmetry in the problem. So there you have it for this harder electric field calculation. We know that in the I hat or j hat notation or direction, we're getting 31,800 newtons per coulomb. All right, so I hit my 50-minute limit. I'm going to stop talking. If you have any questions about this, this was one trivial example, not too bad, but we'll get into some more complicated examples later on that involve actually some integration. So other than that, as always, if you have any questions, please let me know and don't be afraid to ask.